is the modern periodic table, built on the knowledge of hundreds of years of scientific work, experimenting, trial, error, failure, and success. Our job now is to learn how to read this amazing table to the point where you will be able to explain the basics of the periodic table to anyone else. For simplicity, the first thing we will do is pull the middle part of the periodic table out so the most self-evident families are together. We will return to this other section in a bit. This block of elements is called the main group, or Group A. This group contains the most naturally abundant elements of the earth and are the most important for the creation of life. They are also the most commercially produced of all the elements. This group is also known as the representative elements because it best represents the repeating patterns that make the periodic table periodic. It is essentially the main group that gives us the name periodic table of the elements. Imagine we are going to make a periodic table of the crayons using the 8 basic crayon colors that were found in an original crayon box nearly 100 years ago. Red, orange, brown, black, green, blue, yellow, and purple. Now, there are a lot of crayons in this crayon box, but they all basically fall into one of these 8 categories. Okay, first we've got a couple of weird colors here, gold and silver, so we'll put them up here by themselves. Here is the color pattern: red, orange, brown, black, green, blue, yellow, and purple. And then we pick similar colors and do it again. Each row shows the periodic progression of the basic 8 crayon colors: red, orange, brown, black, green, blue, yellow, and purple. The columns are groups of similar colors, basic color families. The basic reds are here, and the oranges are all here, browns, blacks, and so on. And this is exactly what happens when we line up the elements according to the number of protons in the nucleus. Thanks to Rutherford's gold foil experiment and Henry Moseley's graph on atomic weights, we now believe that an element changes by adding a proton one at a time to the nucleus. Adding a proton one at a time increases the electrical charge of the atom, it makes the atom a little heavier, and incredibly changes it into the next element. Now remember, when a positive proton is added to the nucleus, a negatively charged electron is also added to keep the atom's electrical balance neutral. So, like the crayons, we start with a simple grid and begin with one proton. One proton in a nucleus makes the gas hydrogen. And since the proton carries all the weight of the atom, hydrogen is naturally going to be the lightest element since there's only one in there. Helium is the second lightest with 2 protons, and right off the bat, neither of these two really fit into our nice periodic grid, just like the gold and silver crayons didn't really fit either. Oddly enough, hydrogen and helium have no real home on the periodic table, yet it is thought that these 2 elements make up 99% of the known universe. Doesn't that just figure? Helium is usually placed here at the head of the last column, making it a noble gas. Hydrogen is also a gas and is thought to be the most abundant element in the universe. Like 90% of the universe is made from hydrogen, but it has no real home in the table either. There is no other element quite like hydrogen, so occasionally it gets put here above fluorine, making it one of the halogens. Or sometimes over here, but more often than not, it gets pinned at the head of the first column. Leaving these two elements floating on top, like our gold and silver, we get to the third heaviest element with 3 protons in it. And then we begin to start building patterns, very much like our crayon example. Each number represents how many protons are in the nucleus. Thus, this number is called the atom's number, or the atomic number. It is also called the proton number because, well, it tells how many protons there are. Sort of obvious, really. The bigger the number means the element has more protons, and thus the heavier the atom gets. Adding 1 proton at a time, we get lithium with 3 protons, beryllium with 4, then boron with 5. Carbon has 6 protons. Nitrogen is measured as having 7 positively charged protons. Oxygen has 8, fluorine 9, and then neon with 10 protons. Those are like our 8 basic element colors. Then the next element is sodium with 11 protons, and it is very similar to lithium, so we start a new row and a new period. Then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon with 18 protons. The next element is potassium with 19 protons in the nucleus, and it is very much like lithium and sodium, and so we start a new period. Potassium, calcium, gallium, germanium, astatine, selenium, bromine, and finally krypton with 36 protons in the center. Obviously a much heavier element than, say, neon, which has only 10 protons, but it is very similar to neon nonetheless. So each element progressively adds 1 more positive proton to the nucleus, making it a little heavier and, incredibly, changing it into something completely different than the element before or after it. It kind of reminds you of Mendeleev's chemical solitaire, doesn't it? And since the table repeats periodically based on the characteristics of each element, the elements in every column end up having similar characteristics. Just like our periodic table of the crayons. All of the reds are together, all of the oranges are together, browns, blacks, greens, blues, yellows, and purples. Like people in real families have similar characteristics, the way they walk, the way they talk, the way they look, and the way they think. It is just like the columns in our periodic table of the crayons. They have similar characteristics of color, which is similar to the families in the periodic table of the elements. They have similar chemical properties. And the best and most interesting example of element families are at the extreme ends of the periodic table, the 4 outermost columns: alkali metals, alkaline earth metals, the halogens, and the noble gases. The family of elements at the far left side are all highly reactive elements: lithium, sodium, potassium, rubidium, cesium. They are all shiny grayish metals that are so soft you can cut them with a knife like putty. The exposed metal immediately begins to darken as it reacts with the moisture in the air. Now, francium is technically a member of the alkali metals, but we will look at it under the heavy radioactive elements. So what does it mean, reactive? Well, what does it mean if a person is reactive? Quick-tempered, excitable, short fuse? Exactly. Even if a tiny amount of these elements come in contact with water, they immediately react and burst into flame or explode. Like a ferocious lion that needs to be kept in a cage, This family of metals stays submerged in a mineral oil or kerosene cage. If you take them out, they immediately start reacting with the moisture in the air. If you store them in paper, they try to leach the water out of the paper. These are probably not the metals you would make coins with or build a house with. They should probably be called the ferocious metals. Instead, they are given the fairly unhelpful and unmemorable name of alkali metals. Why? Because alkalis tend to form solutions that will neutralize acids, and solutions that neutralize acids are called bases or alkalis. See? Not very memorable. Accurate, but not very memorable. I like ferocious metals because they are ferocious. They are so wild and quick to bond with other elements that they are never free in nature, but are always found safely bonded together with other elements. Now, what about hydrogen? Why is it here? Well, we usually have hydrogen pinned at the top of this column, even though it is a gas. But it is a highly reactive gas, as we all found out. So, even though hydrogen is a gas, it's also pretty ferocious. And under extreme pressure and heat, hydrogen turns into a liquid metal. So, maybe this is a good home for it. They say that the planet Jupiter is under such extreme pressure that its core is actually made of liquid metal hydrogen. So, this column represents the outermost column of the periodic table, the alkali metals family, ferocious. Next door to our ferocious metals is a column with very similar fiery characteristics. They are all shiny metals that are silvery white in color, and though they are all quite reactive, only a couple need to be kept in their mineral oil cage. Beryllium, magnesium, calcium, strontium, and barium. And again, radium is technically a member of the alkaline earth metals, but we will look at this one also along with the other heavy radioactive elements. As a family, they are also quite volatile, but not quite as reactive as their ferocious neighbors. And like their neighbors, they also have an odd name, the earth metals. Actually, the alkaline earth metals, because like their neighbors, they also form solutions that will neutralize acids, alkalis. But why earth metal? Earth metal comes from the old alchemists. The alchemists believed in the 5 essences and thought that since earth doesn't dissolve or melt, anything that doesn't dissolve or melt easily must have a lot of the earth essence in it. And these elements don't dissolve or melt easily. Just look at the difference in the melting point between these two families. Lithium starts melting at 360 degrees Fahrenheit, but beryllium melts almost 2,000 degrees hotter at 2,332 degrees Fahrenheit. Sodium's melting point is only 208 degrees Fahrenheit, but magnesium, 1,202. Potassium, 147. Calcium, 1,542 degrees. Rubidium melts at 102 degrees Fahrenheit, but strontium, 1,407 degrees. And cesium melts at a mere 84 degrees Fahrenheit, but barium, 1,344 degrees. So this family of metals is not only alkaline in nature, but with such high melting points, they obviously had a lot of the earth essence in them. Earth metals, alkaline earth metals, and the name stuck ever since. Alkali is the noun. Alkaline is the adjective that describes the kind of earth metal. Alkaline earth metals. Plus, they're obviously a little more down to earth than their more ferocious neighbors. For example, where sodium and potassium react with room temperature water, magnesium reacts only with steam. So, they are somewhat less reactive, more reasonable, more down to earth than their alkali neighbors. They are the alkaline earth metals. On the far side of the periodic table is the element family that is almost exactly opposite of the families on that side of the periodic table. The table is hedged in by two extremes. On that side, metals. On this side, gases. That side, highly reactive, but over here, highly unreactive, calm and steady. These are the noble gases: neon, argon, krypton, and xenon. They are colorless, odorless, tasteless, and don't readily combine with anything else to form new substances. The noble gases like to stay to themselves. They are steady and even-tempered. Even under extreme conditions, they won't explode, they won't catch fire, they won't combine with anything else, and they don't degrade. They are called noble gases because a noble person is someone who, even under extreme conditions, stays calm. And this family displays a similar noble, dignified attitude, kind of like royalty, or at least what royalty ought to be. If you heat these gases up, they stay just the way they are. They won't react. Many light bulbs are filled with noble gases like argon, because when the filament glows white hot, the gas won't react and get hot and burn up. These gases are inert. They are stable and noble. They are the noble gases. The noble gases are one of my favorite groups, and right next door are another favorite. Because while they are in the same family, they are also unexpectedly different. Plus, they have a great sounding name. The halogens. Sounds kind of powerful and mysterious. The halogens. And they are powerful and they are mysterious. First, they are the only group in the entire periodic table that when sitting around at room temperature have gases, solids, and liquids all in the same family. No other group has a representative from all three states of matter. And unlike the noble gases, they tend to be pretty reactive. The family starts with fluorine and chlorine, two gases, and not just any gases either. Pure fluorine is in fact the most reactive element in existence, even more than any of the ferocious alkali metals on the other side of the periodic table. Whoa. Fluorine attacks so vigorously and wants to bond so energetically that virtually anything placed in the path of a fluorine stream will immediately burst into flames. Fluorine will soon eat through this glass container. It is so aggressive that it will even try to bond with some of the noble gases. If it reacts with everything, what can you possibly store it in? Fluorine needs to be stored in a special metal container made of copper and nickel, and it even starts reacting with that metal. But it quickly forms a layer of hardened fluorine in the inside, which protects the metal from further corrosion. It is also highly poisonous. Chlorine is another gas, poisonous, pale green, with a suffocating, disagreeable odor. Then there is the reddish-brown liquid, bromine. the dark purple crystals of iodine, and finally the black, radioactive, and very rare solid astatine. How rare? The total amount of astatine present in the Earth's crust is estimated at less than 1 ounce. That's not much. This sample of uraninite is thought to contain 1 atom of astatine. That's pretty rare. By appearance, the halogens look nothing like each other, but there are similarities that make them a family. First of all, they are all nonmetals. Second, the temperature at which they melt increases as you move down the group. 128 degrees, 341, 510, 728, and 1067 degrees. They get decreasingly reactive from highly reactive fluorine to the more stable iodine. Astatine, of course, is radioactive, but if for some reason it was not radioactive and you could get enough of it together, it would probably be more stable than iodine. Also, the halogens get increasingly darker as you move down the family, starting at the pale yellowish fluorine all the way down to solid black astatine. Halogen means salt producing because when you mix these non-metal halogens with a metal, it usually produces some kind of salt crystal. For example, when the halogen chlorine is mixed with the metal sodium, it produces table salt crystals. You most often hear about halogens in association with halogen lights, like these lights, which have a small amount of one of the halogens, like iodine or bromine, inside the lamp. As the tungsten element burns, it slowly vaporizes, and over time it gets thinner and thinner and eventually breaks and your light goes out. By putting a bit of a halogen in there, like iodine or bromine, the halogen combines with the tungsten atoms and, incredibly, redeposits some of the tungsten vapor back on the filament wire. This recycling makes the filament last longer and burn brighter. Halogen lights. So, these 4 families are the rows, the columns that hedge in the periodic table. They are the columns that best represent how the periodic law lines up elements with similar characteristics. The ferocious alkali metals and their more down-to-earth neighbors, the alkaline earth metals. The noble gases and their neighbors, the amazing halogens. We will look at the other families in the main group in a moment, but first we want to do a little house cleaning with some of the element names. Obviously, writing out the full names of each element on every periodic table and on every scientific paper would get a little tedious and take up a lot of space. So every element is given a 1 or 2 letter abbreviation. If there are 2 letters in the abbreviation, the first letter is capitalized and the second letter is lowercase. Most of the abbreviations for the elements are simple and make sense. Oxygen is O, osmium is OS, nitrogen is N, neon is Ne, and so on. Actually, there are only 11 elements with abbreviations that you couldn't possibly guess from their names. Just 11. And here they are. Copper, silver, mercury, gold, iron, lead, potassium, sodium, tin, tungsten, and antimony. And here's why their abbreviations are what they are. The abbreviation for copper is Cu, from the Latin word for copper, cuprum. Cuprum is the Latin name for the island of Cyprus, Kypros, where copper was extensively mined in the past. Silver is Ag. It comes from the Latin word argentum, meaning shiny white, for which the country Argentina was named. It means the land of silver, from early legend that there was a lot of silver in that country. There isn't. They aren't even in the top 20. Argentina's largest exports are soy pellets and soccer players. Mercury is Hg from the Greek hydrargyrum, meaning watery silver. You can see it in the word hydra argentum. It's often called quicksilver for that reason, silver that runs. Gold is Au from the Latin aurum and is related to the word aurora, meaning the golden color of the morning dawn. Iron is Fe from ferrum, the Latin word for iron, from which we get the word farrier, one who shoes horses with iron. Ferrum. Lead is Pb from plumbum, Latin for lead, and where we get plumber, since pipes used to be made of lead. Potassium comes from the word potash, and the Latin for plant ash is kalium. Thus, the symbol for potassium is K. In ancient times, leftover plants and trees were burned, and the ash boiled down in huge pots, and the water was evaporated. The resulting white ash was a valuable fertilizer and used as a component to make glass and soap. The symbol for sodium is Na, from the Latin word for soda, natrium. Natron is that white, salty sodium mineral that occurs naturally as part of lake beds in desert environments. Natrum, the Latin word for soda. The symbol for tin is Sn, a word that ultimately comes from this area of Great Britain called Cornwall. Tin was mined from this area since antiquity, and they called this metal stin. The Latin word became stannum, where we get the Sn for tin. But the meaning of the word tin itself has been lost to us in history. The symbol for tungsten is, oddly, the letter W, which stands for wolfram, which is a great name for an element. Wolfram. The word tungsten is Swedish for heavy stone because it is so dense. Tungsten is nearly twice as dense as lead. The word wolfram has an obscure history. When tungsten was first extracted, large amounts of tin were consumed in the smelting process, and a white, foamy froth appeared on the surface. This reminded the scientists of how a wolf foams at the mouth when eating its prey, and so they named it wolf's foam, or wolfram. Both names, tungsten and wolfram, are used for this element, but W is the abbreviation. Antimony's abbreviation is SB. In its powder form, antimony was used by the ancients for use as a cosmetic eyeliner. It was called stibium, meaning a mark, and so its abbreviation became SB. And the real meaning of the word antimony also has been lost to us in history. So let's summarize a bit before moving on. This is the main group. These are periods, and these are columns, just like these are columns. And you know that each period starts with a highly volatile metal, ferocious. As nature adds a positively charged proton to the center of the atom, the element turns into something completely different. Of course, along with a positive proton, a negatively charged electron appears to keep things electrically neutral. A proton is added one at a time until the period ends at a noble gas, and then it repeats. Highly volatile metal ending with a noble gas. You also know that the progressive numbers in each box, 23, 24, 25, 26, 27, 28, and so on, indicate how many protons are in each element's atom. This number is called the atom's number, or the atomic number, also called the proton number. Thus, at a glance, the periodic table tells you exactly how many protons are in each atom's nucleus. Neon has 10, bromine 35, sodium 11, and floating around at the top of the chart are the two lightest elements, hydrogen and helium, the most abundant elements in the universe, but homeless wanderers on the periodic table. The columns end up grouping elements together with similar properties, much like our periodic table of the crayons. And finally, you know that these four columns represent the best examples of how the periodic table groups elements together with similar properties. On the left side, the highly reactive, ferocious alkali metals. And next door, the ferocious but a bit more down-to-earth alkaline earth metals. On the right side, another reactive group, the halogens, with gases, solids, and liquids all in the same column. And finally, on the far right side, the stable and noble elements, the noble gases. Just knowing these few basics gives you a good outline of what the periodic table is and how it works. Now, let's look at the other families in the main group. The final section of the main group is organized a little differently than the four outside families that we've been looking at. Their physical similarities are found in columns, but these families are organized in two triangular blocks divided by a stair-step line right down the middle. This line is sometimes called the aluminum staircase because the top staircase rests on the element aluminum. The two blocks form the poor metals and the nonmetals. Most metals are rich in certain respects. They are shiny, they withstand heat, and they are strong. Structurally, they are rich, like iron. But the bottom triangle of elements are the poor metals. Poor, meaning they don't have the same rich properties of strength like their rich counterparts. They are softer, like this lead. They have a lower melting point, and they tend to fragment easily. They are most useful when added to other elements. The 10 commonly accepted poor metals form the bottom triangle of these elements, and they are aluminum, gallium, germanium, indium, tin, antimony, thallium, lead, bismuth, and Marie Curie's radioactive polonium. That's the bottom triangle, the poor metals. The top triangle is called the non-metals. All of the elements that are not metal like to congregate over in this corner of the periodic table. Now, the noble gases and the halogens are also not metals, but they are so distinctive that they get their own separate column categories. And of course, hydrogen and helium are in their own little non-metal worlds floating on top of the table. The rest of the non-metals are left huddled together in this upper triangle. The 10 commonly accepted non-metals are boron, carbon, nitrogen, oxygen, silicon, phosphorus, sulfur, arsenic, selenium, and tellurium. Now, what do they have in common? Well, nearly everything that a metal is, these aren't. Most metals conduct both electricity and heat really well. These are very poor conductors of electricity and heat. Most metals are generally shiny and malleable, whereas the nonmetals tend to be dull or brittle or gases. They aren't as heavy or dense, and they generally melt or boil at lower temperatures than most metals. Thus, the nonmetals get categorized not so much in what they have in common with each other, but what they don't have in common with everything else. It's even called the not metal category. Now, you might be tempted to say, wow, kind of a loser group on the periodic table, defined by what you aren't rather than what you are. Well, it's true that most of the elements on the periodic table are metals, and only 18 of the elements are nonmetals. But those 18 elements make up 85% of our Earth's crust. 99% of our atmosphere, and 99% of our oceans. In fact, 98% of all living organisms, including you and me, are made up of these precious 18 non-metal elements. All of a sudden, the non-metals seem pretty important now, don't they? And they are. Now, some textbooks will categorize these elements in columns, like the oxygen group, because oxygen leads the list, and the boron group, because boron leads the list, and so on. But this grouping is not all that common. But sometimes you will see a chunk taken right out of the middle of these two groups, following the line of the stair step. Boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Although they belong to their groups of poor metals and nonmetals, there's something special about these 7. They look and act like metals, but only sometimes, when the conditions are right. When pulled out like this as a separate group, they are called metalloids, which literally means sort of like metal. Just like android means sort of human. Android, sort of human, metalloid, sort of metal. Arsenic and antimony look shiny like metal, but they are poor conductors of electricity. Better than nonmetals, but not as good as regular metal, like sort of a metalloid. Or take the most famous metalloid, silicon. Silicon looks shiny and lustrous like metal, but it is brittle and prone to chipping like glass. Silicon also conducts electricity, or insulates against electricity, depending on how much electricity you apply and what you mix in with the silicon, which is why it is also called a semiconductor, and why silicon is used in silicon chips to make computers. Dig up sand, which is mostly made of silica, which is silicon combined with oxygen. Heat the sand to separate out the raw silicon and melt the silicon in a furnace to liquefy it. Using a seed of silicon, form the molten element into a solid silicon ingot crystal weighing about 450 pounds. Slice the ingot into dime-thin discs and buff it to an absolute mirror perfection. Coat them with special chemicals and etch microscopic switches into the semiconducting silicon in a room that is 1,000 times cleaner than a hospital operating room. Cut it out of the disc and put the chip into a processor package to protect it. Then plug it into your computer. A silicon chip the size of your fingernail will hold 1 billion transistors. From sand to a computer chip in 3,000 unbelievably complex steps. A computer chip is, without question, the most complex manufactured product on Earth. Silicon. It looks like a metal, but often behaves like a non-metal. It's sort of like a metal. It's a metalloid. That is the main group of the periodic table, also called the A group or the representative group. 4 families at each end: ferocious alkali metals and their reactive but more down-to-earth neighbors, the alkaline earth metals. The reactive and very diverse group of the halogens, with liquids, solids, and gases all in one family. And the noble gases. Steady, unreactive, noble. The 2 triangle groups, poor metals and the non-metals. And finally, the hidden stair-step in between, containing the metalloids. The main group of the periodic table.